So we were discussing various theorems about the integrability of the functions, namely given two integrable functions, what can we say about the sum of those two functions, etc. Okay. So let us list similar properties or similar theorems, or as has been done by Rudin, we will just state one theorem which includes all of those. Okay. Okay. So first we had said that if f and g are integrable, or AB alpha, then f plus g is also integrable, and integral a to b f plus g d alpha is same as integral a to b f d alpha plus integral a to b g d alpha. Okay. And also in this itself I will say that if k is a real number, then k times f is integrable, and we can say similar thing about the integral of k times f. So that is integral a to b k f d alpha, that is same as k times integral a to b f d alpha. Okay. As I mentioned earlier, this whole thing can be said in just one single sentence if you use the terminology of linear algebra, namely that this is a vector space, or that is set of all integrable functions is a vector space, and the map which takes a function to its integral is a linear functional on that vector space. Okay. We can say something more. Okay. We have seen these two properties yesterday, and its proof also. There are other properties which are very similar to this, and the proofs are also very similar. So we will simply state, okay, and we will not go into too many details of the proof. Okay. For example, again, suppose we take say two such things. Let us say we have two functions, if f and g belongs to this R a b alpha, and suppose f is less than or equal to g. F is less than or equal to g means what? At each x in AB, fx is less than or equal to gx. Okay. Okay. Then integral of f is less than or equal to integral of g. That is what we should expect. Okay. Then integral of AB f d alpha is less than or equal to integral of AB g d alpha. Okay. Another way of expressing the same thing is that this is a positive functional, that is, this defines a partial order on this vector space. Okay. And this functional respects that partial order. If f is less than or equal to g, integral of f is less than or equal to integral of g, and you can see that the proof will be very straightforward of this. Just compare the upper and lower sums with respect to f and g. Okay. You can say that for every partition up f alpha will be less than or equal to up g alpha. Okay. That is easy to see because of this. Okay. Because f less than or equal to g, and it will follow from here. Okay. That this will follow. So in fact once you understand the proof of this, okay, all other proofs are similar, that is why we shall not spend too much time in discussing those proofs. Okay. Another thing is that, which is again a very well known property of the integrals, that if you take some point in the interval, suppose I call that point C. Okay. Let us say so. Okay. Let us take let a less than c less than b, and then if f is integrable over AB, that is if f belongs to R AB alpha, then f is also integrable over AC, it is also integral over CB, and the corresponding integrals, their sum is same as integral over AB. That is, then f is integrable over this interval AC, also f is integrable over the interval CB, and integral a to b f d alpha is equal to integral a to c f d alpha plus integral c to b f d alpha. Okay. All right. Only thing that is required to prove this is that the partitions that you are considering should contain this point C. Okay, partitions that you are considering should contain. If it does not contain, fine, you add that point C, that will be a refinement, and use the property of the refinements of the upper and lower subs. That is the only thing. So once the partition contains the point C, then you can see that the upper sum which corresponds to this integral will be sum of the upper sum which corresponds to this integral plus upper sum which corresponds to this integral. Okay. And that is all is the observation here. Okay, right. So that's all that you need to prove this as well as this. Okay. In fact, the converse is also true. In fact, I should say that if f is integrable over both AC and CB, then it is integrable over AB. Okay, and then also this follows. Okay, so instead of writing if this happens then this happens, one can also use this if and only if. Okay, that means this way is also true and that way is also true. Okay, and in this case we can say that is whenever any one of these is true, and in this case is true. Okay. All right. Then one more thing we can say, that suppose we find some number which is okay, let us say let f belongs to R AB alpha. Suppose f is integrable and suppose k is some number. See, once we say that f is integrable, it means it is bounded. Okay, we are only talking integrability of bounded functions. So if f is bounded, mod f is also bounded function. So we can find some number such that mod f t is less than or equal to that number for each t in AB. Okay, so let us say f is integrable and mod of fx is less than or equal to k for all x in AB. Then this absolute value of integral a to b f d alpha, this is less than or equal to k times alpha b minus alpha a. Okay, this is less than or equal to k times alpha b minus alpha a. Well, okay, I mean this is also fairly easy to see. See, remember we have shown this already, that is small m into alpha b minus alpha a. For any partition, this is less than or equal to LPF alpha, and this is less than or equal to UPF alpha, and this is less than or equal to big M into alpha b minus alpha a. Okay, this is what we have shown for any partition P. Okay, and we know that when the integral exists, that should lie between these two values. Okay, so that means this should be less than or equal to integral a to b f d alpha. Okay, right. Okay, now what is this number k? It has a rotate mod fx is less than or equal to k. Okay, and what is this number big M and small m? We know that fx is less than or equal to this big M. Okay, so depending on if m is depending on whether m is positive or negative. Okay, and similarly depending on whether this m is positive or negative, this k can be one of these. In fact, you can say that this k can be one of these four values, plus or minus m or plus or minus big M, right. Do you understand this? Okay, for example, suppose fx lies between, let us say fx lies between, let us say minus 2 and 9, let us say. That means what? Small m is minus 2 and big M is 9. Okay, but if that is the case, then mod fx is less than or equal to 9. Okay, mod fx is less than or equal to 9. Okay, right. On the other hand, so 9 is nothing but M. Okay, on the other hand, suppose it is something like this, let us say it is between minus 9 to 3. Okay, in that case big M is 3, small m is minus 9, but then you can take k as 9 because mod fx will be less than or equal to 9. Okay, So k will be 9. So this k will be one of these 4 values, plus or minus m or plus or minus big M, and we already know this, that integral a to b f d alpha is less than or equal to this. So this is also less than, you can say this is less than or equal to k into alpha b minus alpha a, and this is also bigger than or equal to minus k into alpha b minus alpha a, and that will prove this. Okay, all right. Now so far we have said so many things about taking various functions f, g, etc. Okay. Now we will say similar things about this function alpha, okay, that is the function with respect to which we are taking the integrals. Suppose we take two functions, alpha 1 and alpha 2. Remember here this alpha we always take monotonically increasing function. So what can we say about something like, say, integral f d with respect to alpha 1 plus alpha 2, etc. Okay. So one can expect that should also be the sum of the two corresponding integrals. Okay. So what we would say is this, that suppose alpha 1 and alpha 2 are monotonically increasing in AB, then okay, let us say increasing in AB. Okay, if f is integrable with respect to alpha 1 and also with respect to alpha 2, then f is integrable with respect to alpha 1 plus alpha 2. Okay. So if f is, let us use symbols, if f belongs to R AB alpha 1 and f belongs to R AB alpha 2, then f belongs to R AB alpha 1 plus alpha 2. But that is not all, we also want to say something about the integrals. Okay. Okay. So I will continue here. And integral over a to b f d alpha 1 plus alpha 2 is same as integral a to b f d alpha 1 plus integral a to b f d alpha 2. And again, see, only thing that you have to notice here is that whenever alpha 1 and alpha 2 are monotonically increasing, alpha 1 plus alpha 2 is also monotonically increasing. So this makes sense. And so if you compare the upper sums or lower sums, so if you take the upper sum with respect to alpha 1 plus alpha 2, that is going to be a sum of the upper sum with respect to alpha 1 and upper sum with respect to alpha 2. So it will be essentially exactly the proof like this, okay, similar to this. Okay. Okay. Now let us also look at an analog of this. Here we have taken k times f. Okay. Right. So similarly we can think of k times alpha. Okay. Suppose we take k times alpha, there is a slight problem here. Okay. If alpha is monotonically increasing, k times alpha need not be monotonically increasing. Okay. So what is the restriction that we require for that? K should be positive, right? So then with that restriction it is okay. Of course if k is equal to 0, the whole thing is trivial. Okay. So you take a positive number k, then we can say that if f is integrable with respect to alpha, and if you take k as a positive number, then it is also integrable with respect to k times alpha, and a similar relation will hold. So one can say that, so let alpha be monotonically increasing and k is strictly bigger than 0, then what we want to say that if f is integrable with respect to alpha, then f is integrable with respect to k times alpha, and you have a similar relationship between the integrals, integral a to b f d k alpha, this is same as k times integral a to b f d alpha. Okay. That means the constant k will go outside the integral sign, whether it is k times f or k times alpha. Only thing is that if it is k times alpha, you have to have this restriction, k must be positive constant. Okay. Right. Of course, this restriction is because till now we have considered integrals only with respect to monotonically increasing functions. Okay. Suppose we remove that restriction, suppose we have find some way of considering the integration with respect to other kinds of alphas, then this restriction also can be removed. Okay. But that we shall discuss sometime later. Okay. For the time being, we shall stick to monotonically increasing functions. Is this okay? All right. Okay. Again, here also there is nothing much in the proof. You have to just look at the corresponding upper and lower sums. All right. So as I said earlier, since the proofs of all these other things are very similar to what we have done here, we shall not go into details of those proofs. Okay. Now it leads to some other natural questions. Okay. We have taken the sum f plus g. What about the product? Okay. Suppose we know that f and g are integrable, then can we say that the product is also integrable? And then by product one can ask several such questions. There are several other ways of combining the two functions or constructing a new function from a given function f. So in which case we can say that a new function will also be integrable. Okay. So what we shall do is that we shall prove one good theorem in that respect, and several such cases like product etc. will turn out as a corollary. Okay. Basically what we want to prove is that if you compose with a continuous function, suppose you take an integrable function and if you compose it with a continuous function, then composition also will be integrable. Once we prove that, all these other things about the product etc. will follow from that. Okay. So let me just go back here and state that theorem. Okay. Okay, so let us say that we start with this. Let us say f is integrable with, as usual, alpha is monotonically increasing and f is integrable with respect to alpha. And we want to, okay, let f belongs to this. So we want to compose this f with some continuous function. Okay. And as you know, if you want to compose a function, that function must be defined, or the domain of that function should at least contain the range of this. Okay. But we know that if we use the usual notation, we know that the range of this is contained in the interval small m to big M, right? That is what we are saying, that small m is the infimum and big M is the supremum. So if any function is defined on the interval small m to big M, then we can talk of composition. Okay. So let f belongs to RAB and phi belongs to C will use the, as usual, set of all continuous function on this interval C small m to big M. Okay. And suppose we give some name to this composition, we call H as phi composed with F, H as phi composed with F. That is okay. If you, for your satisfaction, let us write the full form. That is what we mean is H at x is equal to phi of fx for each x in AB. Then okay, then H is, that is the conversion, then H is Riemann integrable, it is not Riemann, then H is Riemann Stieltjes integrable with respect to the function alpha. Of course, in this case we cannot give any formula for the integral of H in terms of integral of f and phi etc. Okay. We cannot say anything like integral of H is something like phi composed with integral of f and any such thing. Okay. Right. Though of course the value of the integral will also lie between small m and big M multiplied by alpha b minus alpha etc. But we can't say any such thing about the values of the integrals. Unlike here, for example, here for case in all such cases, apart from saying that the certain functions are integrable, we have also related the values of the integrals. Okay. but this is a different theorem. Here we cannot say anything about what any relationship about integral of h and integral of f, okay, but that is okay, okay, we just want to say that it is integrable, okay, alright. Now to look at the proof of this, okay, let us start with this. First of all, this function phi is continuous on this interval small a. This is a compact set, okay, and every continuous function on a compact set is uniformly continuous, something that we have been using again and again in the theory of integration. So we shall use that here also, okay. And what is it that we want to show? We want to show that this h is integrable, and we shall use the standard technique to show that given epsilon you find a partition such that the difference between upper and lower sum is less than epsilon or some constant multiple of epsilon, okay, that is okay. So let epsilon be bigger than 0. So our final aim is this, that we want to find a partition such that with respect to that partition upper sum of h minus lower sum of h should be less than epsilon, or okay, as I said some constant multiple of epsilon, okay, all right. Okay, but on the other hand this phi is continuous, so corresponding to this epsilon there will exist delta, we can say that there exists delta bigger than 0 such that if you take any two numbers in this interval whose difference is less than delta, then the difference between the corresponding values of h is less than epsilon, okay. There exists delta such that for all s and t in this interval small m to big M satisfying mod s minus t less than delta, we have mod hs minus ht is less than epsilon, okay. Oh sorry, phi s minus phi t, you are right, phi s minus phi t, that is correct, phi s minus phi t is less than epsilon, okay, alright. Then what we also know is that in all such argument, if some delta works for this, if some delta satisfies this, then any number smaller than that will also have the same property, right. We can suppose you have chosen one delta which satisfies this relation, that is whenever mod s minus t less than delta, then mod phi s minus phi t less than epsilon. Instead of delta, suppose I replace it by delta by 2 or delta by 3 or any number smaller than that delta, still this property will be true, okay. So that is why I can in particular assume that this delta is smaller than epsilon. Do you agree with this? Because that is something we may need in the subsequent calculations. So I will assume that delta is less than epsilon, okay. So as usual this such a thing is called without loss of generality, okay? Without loss of generality we may assume delta is less than epsilon, okay. Till now we have only used the continuity of this function phi, right, whatever we have done here it follows merely by the continuity of the function phi, but there is one more thing that we know, namely that we have assumed that f is integrable, that is something we have not used yet, okay. F is integrable, so that is something we have not used yet. So we can say that because f is integrable, given any positive number we can find a partition such that the difference between upper and lower sum with respect to that partition is less than that positive number, okay. So we can say that since f is integrable, there exists a partition P such that what should happen if you take this UPF alpha minus LPF alpha, this should be less than whatever number I take, okay, epsilon, delta, or okay, whatever positive number. So here I will take that as delta square, okay. Why delta square? That will become clear to you when we proceed with the proof, because we are not interested in this difference. we want to show that UPH alpha minus LPH alpha is less than epsilon. So this is just a preparation for that, okay, alright. Okay, remember one more thing, this is nothing but sigma, okay, if the partition P is this, P is less than x naught, so P is equal to x naught, x1, xn etc., then this is nothing but big mi minus small mi into delta alpha I, right, I going from 1 to n. Okay. All right. Okay. Now, what are we interested? We are interested in, okay, we are interested in similar difference between, that is, we are interested in not UPF alpha and UPH alpha, but we are interested in UPH alpha minus LPH alpha, right, that is what we want to show, that that is less than, but what is that, let us just write the value of that, okay, UPH alpha minus LPH alpha. What will be this? We will have to define the new numbers corresponding to the function h, right, we will have to define the new numbers corresponding to the function, this mi and, okay, this big mi and small mi correspond to the function f, okay, let me write it here, big mi is the, what is that, supremum of fx, where x belongs to xi minus 1 to xi, okay. So what we want is similar number for the function h, okay. So suppose I call that number mi star, that is, I will write supremum of hx for, okay, x belongs into this same interval, okay, and similarly small mi star is infimum of, okay, I will use some, okay, for infimum of hx for same x belonging to xi minus 1 to xi. So using this notation, UPH alpha minus LPH alpha, that will be nothing but sigma I going from 1 to n, big mi star minus small mi star, big mi star minus small mi star, multiplied by delta alpha I. Okay. All right. Now we want to show that our aim finally is to show that this sum is this difference UPF, this difference which is nothing but this sum, that can be made arbitrarily small, okay, that is less than epsilon or epsilon multiplied by some constant etc. Okay. Now to do that, again we will have to use what we have done here, okay, that is, we have seen that this, if for this epsilon there exists a delta bigger than 0, such that whenever mod s minus t is less than delta, mod phi s minus phi t is less than epsilon, okay. Now what is h? H is phi composed with f, okay, remember, let us just see, that is, see, let us just picturize this, suppose this is the interval ab, right, this is the given interval, okay, and suppose this is the interval small m to big M, okay, f goes from here to here, right, f goes from here to here, okay, and then h is defined on here, okay, it may go to somewhere, okay, it does not matter, h is defined here, okay, alright. Now what we know is that if the difference between any two values here is less than delta, then the difference between the corresponding values there will be less than epsilon, okay, not h, this is phi, right, okay, that is phi, right, this is phi, okay. In other words, if I know that this big mi minus small mi is less than delta, then for the corresponding value big mi star minus small mi star will be less than epsilon, right. big mi star minus small mi star will be less than epsilon, okay, right. Because what is the meaning of that? Big mi minus small mi is nothing but the corresponding, because this is the value that f we take, okay. So just tell me whether you agree with this. If big mi minus small mi is less than delta, then big mi star minus small mi star is less than epsilon, okay. Just tell me whether you agree with this. Okay, okay. What is big mi? Big mi is the supremum of fx, where x lies between xi minus 1 to. See, just as I have done this interval a to b, suppose I take the interval xi minus 1 to xi, that is some subinterval, okay, right. Is it clear that this image of this interval under f will be small mi to big mi, right, because small mi is the minimum of fx when x varies from xi, okay. So fx, when x varies between xi minus 1 to xi, fx will vary between small mi and big mi, okay, right. Now we know that if this difference is less than delta, okay, so phi of that, suppose you take any, that means if this difference is less than delta, phi mi minus phi small mi, that will be less than epsilon, okay, or for that not only phi mi minus phi mi, for any two values that lie in this interval, corresponding difference phi s minus phi t is less than epsilon, okay. That is how we took this, delta, okay, all right. There is only one problem here, okay. This may not happen for all I, okay, because we do not know anything about the function f, okay. This may not happen for all I, so we have to split, okay, we have to split these indices, that is this set, there are n such intervals, so we have to split these indices, those I for which this happens and those i's for which this does not happen, okay. So suppose we take this set I 1, 2, etc. up to n, okay, there are n such intervals, let us say I belongs to any of this, okay, okay. Then what I will say is that, okay, you can give some name to this set, suppose I call this set as j suffix n, so I will take one set A as the set of all those I in this j suffix n, such that this big mi minus small mi is less than delta, okay. And for those I know that big mi star minus small mi star is less than epsilon, okay, all right. And then the remaining set, suppose I call this B, for which this does not happen, okay, okay. So one can say that I will set sigma I belonging to Jn, this does not happen means what, big mi minus small mi is bigger than or equal to delta, okay, big mi minus small mi is bigger than or equal to delta. So all right, okay. Now come back to this sum here, okay. This up h alpha minus lp h alpha, this is sigma I going from 1 to n, this mi star delta alpha I, etc. I will split this sum into two, okay, I belongs to A and I belongs to B, that is what I will say is that this is same as sigma I belongs to A big mi star minus small mi star into delta alpha I, okay, and plus, remember A union B is Jn, okay, every I from 1 to n has to either belong to A or to B, okay, every I has to either belong to A or to B, okay. So sum I going from 1 to n is same as sum of those indices for which I is in A plus sigma I belongs to B big mi star minus small mi star into delta alpha I. Okay, do you agree? Okay. Now out of these two parts, I know that at least for this part this big mi star minus small mi star is less than epsilon, okay, right, okay. So we can say that this is less than epsilon into epsilon into sigma I belonging to a delta alpha I, and sigma I belonging to a delta alpha I is, you can say, sigma I belong less than or equal to sigma I belongs to j and delta alpha I, and so which will be ultimately less than or equal to alpha b minus alpha a, okay, right. So this part is less than epsilon into alpha b minus alpha a. Okay. All right. So now the question remains, what do we say about this, okay, what do we say about this, okay. Now here you can easily see the problem, we cannot say anything about big mi star minus, it is not less than epsilon, okay. But since we cannot say anything about this, what we will do is that we will have a control over this length sigma delta alpha I, okay, and let us see how does that follow. We can see one thing here, that is, okay, again look at this, okay, look at this equation here, okay, sigma I going from 1 to n mi minus mi delta, let me write this equation once again here, okay. What is the equation? Okay, I will write it the reverse way, okay, this delta square is bigger than, okay, bigger than sigma I going from 1 to n big mi minus small mi into delta alpha I, okay, all right, okay, all right, that is the thing. I have just written this equation once again, okay, that is all, not equation, inequality, I have written this inequality once again. Now do you agree that this, suppose I take this sum I going from 1 to n, that has to be bigger than or equal to sigma I belonging to b big mi minus small mi delta alpha I, right, right, because you are just taking a few of these terms, okay, ignoring those terms which belong to, for those terms which correspond to I belonging to a, right, okay. But what do we know if I belongs to b, what do we know about this big mi minus small mi? That is bigger than or equal to delta, okay, that is bigger than or equal to delta, that means I can, each of this sum is bigger than or equal to delta times this delta alpha I, okay. So what we can say is this is bigger than or equal to delta times sigma delta alpha I for I belonging to b, okay. So what does this prove? That delta times sigma delta alpha I is less than delta square, okay, which means this sigma delta alpha I is less than delta, right, that is sigma delta I, that is sigma delta alpha, of course it is not for I going from 1 to n, it is only for I belonging to b, okay, that is for those intervals which corresponding to I belonging to b, if you take the sigma delta alpha I for I belonging to b, that sum is less than delta, okay, that sum is less than delta, okay, right. Now you will understand why we took delta square here, okay, now you understand why we took delta square here, okay, all right. Of course delta to the anything bigger than the power 1 would have done, okay, but this, all right. So if I now look at this sum, I do not know anything about this mi star minus mi star, but I know that the sigma delta alpha that is less than delta, and we already assumed that delta is less than epsilon, okay, we already assumed that delta. So only thing remains is what do we do about this mi star minus small mi star, but you can say that phi is a, after all what are these mi star and big mi star, okay, those are the values of this hx, okay, but hx is phi of fx, okay, hx is phi of fx, right. So but phi is a continuous function, phi is a continuous function, so and continuous function defined on this closed body interval, so phi is bounded. So as we had done earlier, we can say that I can always take some number k such that mod phi x is less than or equal to k in that interval small m to big M, okay. So we can say that there exists k bigger than 0 such that mod phi t is less than or equal to, sorry, mod phi t is less than or equal to this big K for all t in the interval small m to big M. Okay. All right. Then what can you say about this mi star minus big mi star minus small mi star? Do you agree that this will be less than or equal to 2k? Each of them is less than or equal to, see, mi star, remember again look at the difference. What was mi star? Mi star is supremum of hx. What is hx? Hx is phi of fx. Okay, hx is phi of fx, right? Okay, so phi, and we know that for any x mod phi, for any t mod phi t is less, so in particular phi of fx is mod phi of x less than or equal to k for any k. So in particular mi is mod mi is less than or equal to k, mod small mi, sorry, mod mi star is less than or equal to k, mod small mi star is also less than or equal to k, and hence we can say that this, therefore this means that big mi star minus small mi star is less than or equal to 2k. For this is true for all I, not necessarily for I in B, but for I in A or etc. Okay. Basically what we say is that since mod phi t is less than or equal to k, if you take any two values of t, then the difference or sum or whatever will be less than or equal to 2k. Okay. All right. So we will use that here. Okay. We will use that here. So this second part is less than 2k times delta, right, because each of this is less than 2k, less than or equal to 2k. So that 2k will come outside, so 2k times sigma delta alpha I going to be, okay, all right, I will write that one more step here. Okay. This is less than 2k times sigma I in B delta alpha I. Okay. And we have already shown that this part sigma delta alpha I is less than delta, okay, sigma, okay, and we have already chosen delta to be less than epsilon. So in fact here itself I could have said that sigma I belonging to be this part is less than epsilon. Okay. So what does it mean? That this whole thing is less than epsilon into alpha b minus alpha a plus 2 times k. Okay. Alright. So okay, let us again take the, what did we show? We started with an epsilon bigger than 0, okay, and corresponding to that we produced a partition P such that with respect to that partition P, u p h alpha minus l p h alpha is less than epsilon into this number. Remember this number does not depend on anything, okay, it is alpha b minus alpha a plus 2k, okay, 2k is the just the number which depend on the function phi, okay, it does not depend on the partition, okay, right. So this is just an absolute constant multiplied by epsilon, okay, so that shows that the function h is integrable. Okay. Of course there are so many things that are involved in this proof, namely for example choosing this partition with this kind of property and then observing that the sum of those delta alpha or I belonging to B becomes less than delta etc. So this construction is involved. So what I suggest is you have a close look at this proof once again on your own afterwards, and if you still have any doubts etc. we will discuss those things in the class. Okay. Alright. Okay. Now I said that once you prove this you can take care of many other things, which for example products of functions etc. Let us see how that can be done now. Okay. Okay. I will write it as a corollary. okay, there are several things. One is this, let suppose we take two functions, let f g belonging to this R a b alpha, that is f and g both are integrable, then earlier I had remarked that this is a vector space, okay, this is a vector space. Now when you prove this, it will also mean that the product of elements is also there. So not only it is a vector space, it is also a ring, okay, it is also a ring, and such things are called algebras, okay, a vector space on which a product is also defined, and that product should also satisfy some extra axioms with respect to the vector space operations, then that is called an algebra. But okay, let us not go into those things now. Let us see how this can be proved. In fact, if you have a first look, you will see that there is no relationship between this and this, right, okay, because you cannot get fg by given two functions f and g, you cannot get their product by composing with some function, right, okay, but that is not how we proceed also, okay. So what we do is as follows. Suppose I take phi of t is equal to t square, suppose I take phi of t is equal to t square, okay, and compose this phi with f, okay, what will be the result? It will be f square, right, okay, that is if I take the function phi t is equal to t square and then phi composed with f is nothing but f square, okay, because phi of ft is nothing but ft square, right, phi of ft is nothing but ft square, so that is same as f square, that is how we will define the function f square. But now, but is this a continuous function? Phi t, whatever be is the interval, phi t is equal to t square is a continuous function, which means if f is integrable, f square is integrable, right. So this means that f square is integrable, f square belongs to this R a b alpha. But then in the same way I can say g square is also integrable, right, okay, if you compose phi with g, you will get g square, okay, so similarly g square also belongs to this. So what we, okay, in fact, alright, so what we say is that whenever a function is integrable, its square is also integrable, right, okay. And then f plus g square is also integrable, right. We already shown that if f is integrable and g is integrable, then f plus g whole square, f plus g is also integrable, and hence f plus g square is also integrable, okay. So you can either say from here that this, you can take this minus f square minus g square, this is also integrable, okay, and that is nothing but 2 times fg. So this, okay, fine, so this divided by 2 is f into g, okay. So all that we are using here is that if a function is integrable, its square is also integrable, okay, and we already proved that f plus g is integrable, so f plus g square is integrable and f square and g square are integrable anyway, okay. So this is also integrable again, okay, we already shown that the sum of the two functions is integrable and all that, okay, alright. So this follows, okay, alright. One more thing, in a similar fashion, let f be integrable, then mod f is also integrable, okay, okay. Now what is the obvious way to show that? You just take phi t is equal to mod t, okay, you just take phi t is equal to mod t, that is a continuous function, and so phi composed with f is nothing but mod f, okay, phi composed with f is nothing but mod f, okay. But in this case we can say something more about this integral of mod f, okay, and that is the following, okay, and we can say this: if you look at the absolute value of the integral, that is integral a to b f d alpha, then that is less than or equal to integral a to b mod f d alpha. Okay, but this part is trivial. Okay, once you understand that mod f is integrable, see, remember we have already proved that if you take two functions, f is less than or equal to g, then integral of f is less than or equal to integral of g. Okay, we just use that fact. Okay, for example, we know this, that f is less than or equal to mod f, right, whatever be x, fx is less than or equal to mod f, and similarly it is bigger than or equal to minus mod f. Okay, so integral of f will be less than or equal to integral of mod f, okay, and it will be bigger than or equal to integral of minus mod f, okay. So that shows this, right, okay, integral of f plus or minus integral of f d alpha is less than or equal to integral mod f, okay, right. So for example, this shows that integral f is less than or equal to integral of mod f, and this part shows that integral of minus f is also less than or equal to integral of mod f, okay. So that means, and whichever is the bigger is the absolute value, so this is less than or equal to integral of mod f, is it clear? Okay, so we will stop with that. Tomorrow we shall see the integral as a limit of a sum. So till now we have been only discussing the integrals in terms of upper sums and lower sums. Though we have introduced this Riemann-Stieltjes sums, we have not made any use of those till now. That relations we shall see tomorrow.